Hello and welcome to this course on MATLAB programming for numerical computations. We are doing bonus lectures for differential algebraic equations in week 10 of this course. This is the last lecture of this series and I am going to talk about some extensions and also recap some of the things that we have talked about with respect to differential algebraic equations. Okay. So, these were the three examples that we took of the differential algebraic equations, and one of the things that over the years students have asked is something that I am going to discuss right away. Okay. So, let us take this particular example. So, you have dy by dt equal to x and 0 equal to x minus y sin t. Okay. So, if your equation is in this form, you can always rearrange this equation to write this as x is going to be equal to y sin t. You can substitute it over here and you will get dy by dt equal to y sin t. Okay. So, you have example number 1 is DAE, you have example number 2 which is ODE. Okay. What is the difference between the two? Okay. There is no difference between the two. In this particular example, because you had a direct relationship between x and y sin t that you could obtain, as a result you could easily substitute it into the first equation. Alternatively, what you can do is something that we have done for the definition of the index of the DAE. Okay. So, if we differentiate this equation, we are going to get 0 equal to dx by dt minus dy by dt sin t minus y cos t, or you can take dx by dt onto the other side and you will get this, and you can substitute dy by dt equal to x and you are going to get x. Okay. So, our third set of equations is going to be dy by dt equal to x Okay. Now, again equation number 3 is also equivalent to equation number 1 and 2. Okay. So, it is very much possible for you to solve equation 1, or you can solve equation 2, or you can solve equation 3, and all of those are equivalent for a problem like this. Okay. Now, let us take a look at example 2. Okay. In example 2, what happens is you have a higher index DAE, and index 2 DAE there is cannot be solved ODE 15s. You can't solve that using ODE 15s. So, you will have to do some kind of a modification to that problem. Why? Because over here x is not explicitly specified, but x is implicitly given. So, what you can do definitely is you can differentiate this equation once, and as we had shown earlier in the first lecture of this bonus set, once you differentiate this, you will get the second equation in terms of x. Then you have index 1 DAE and you can solve it using ODE 15s. So, in the third example, just as we had done earlier, this equation, the second approach is going to be x3, you can write it as okay. So, this becomes a known equation for x3, and you can substitute x3 into these, and now you will get to solve dx1 x2 by dt equal to f of t comma . Okay. This is very much equivalent to this particular approach that I had shown, where the algebraic equation you substitute into the original differential equations. The third approach, again you can do the same. You can differentiate this equation and you will realize that what you get is dx1 by dt plus dx2 by dt plus dx3 by dt is going to be equal to 0. Okay, this is what you are going to get. So, dx3 by dt is going to be just negative of x1 dash plus x2 dash. You add those two and you will get dx3 by dt this is going to be dx3 by dt. Okay. So, now what you have is you have d by dt this guy and okay. So, that is how you can get. Okay. Now, you might be tempted in general to want to solve this equation using this particular approach. Okay. In both these example 1 as well as example 3, you can very well go ahead and solve it using this approach. There's no harm in doing that. But there are certain problems where these approaches it's infeasible to use these approaches. Let us say we have a reaction of A and B. In fact, one of the things that we do in our research is a reduction of CO2 to address the global warming problem. So, CO2 plus hydrogen can be used to form methanol. Okay. So, this is one of the things that we do in our research. Okay. Now, the reaction rate for this, okay, is going to be something like K multiplied by it's actually partial pressure, but I will replace it with concentration. The expression has this particular form. Okay. The equations that you get is of the form I will put bars over here. Okay. So, this is the type of equations that you get. So, these are differential equations, these are algebraic equations. As you can see, R is a fairly complex expression. Okay. So, it is going to be very difficult to take a pen and paper and hand solve the algebraic equations in order to express this particular R, okay, to get, and therefore to get C bar and then substitute C bar into this equation. That is actually quite difficult to get. Likewise, if you have an expression of this form, differentiating it is actually going to be much more tedious, and you will be left with much more complicated equation in order to solve. Okay. So, in an example like this, we actually do not have an option as we had in these two examples that I have shown. In these two examples that I have shown, of course, there is options, because in both these examples you could express x or x3 in terms of y or x1 and x2, or you could differentiate it easily, and the differentiated equation was easier to solve than the original algebraic equation. But these are the problems, for example, in our research we face all the time, where either it is not possible to convert the differential algebraic equations into direct expressions, or differentiating the algebraic equations will result in an expression that is way more complicated than the original equation. In that particular case, we have to resort to solving differential algebraic equations. If we had this equation in the form and then we have this mass matrix. What is this mass matrix going to look like? It is going to be 1 0 0 0. So it's dCO2 by dZ, dH2 by dZ, there is nothing d by dZ. This is going to be our mass matrix, and then we can solve that using ODE 15S. Okay, let's go back and look at what we had done with these two guys. Okay, with these two, what we had done is we had written the mass matrix, okay. So this is how we had solved this. Okay, this part okay. So this is what we had done. The right hand side of the equation, we treated it exactly the way we treated ordinary differential equations. You have had a fair amount of experience using ordinary differential equations. We did that in week number 7, we did that in week number 8, we did that again in week number 10 in case of solving boundary value problems. It's the exact same approach for treating the right hand side. The left hand side has a mass matrix. The mass matrix is assigned using the command ODE set. With ODE set, once you assign the mass matrix, rest of the solution of differential algebraic equation using ODE 15S remains exactly the same. Once you solve the DAE, you are going to get the solution that you can then interpret it exactly the way we interpreted our ODEs in week 8. Okay. So that's basically what I wanted to cover in this particular additional set of lectures. So with that, I come to the end of this lecture, and indeed to the end of this bonus lecture series. I thank you for watching, and if you have any questions, please post them in the forum or ask them in the live session. Thanks and bye.